Welcome back to the lecture series on heat transfer operation. This is Yogesh Lange. In this video, we introduce about the convection. What is meant by a convection? The module number 2 is on the heat transfer operation by convection. In the last module, that is in a conduction, we learn the basic modes of heat transfer, that is conduction, convection and radiation. Now the conduction, we see the definition of the conduction. What do you mean by conduction? Then which law is applicable for the conduction? That is the Fourier's law is applicable for the conduction. And we learn the steady state heat transfer and the unsteady state heat transfer in the conduction part. Now this module is deal with the convection one. Now what is meant by a convection? So let's see the contents from this module. We will learn from this module, it is the fundamental consideration in the convective heat transfer. What are the fundamentals in the convective heat transfer? As in the conduction one, we see the heat transfer by the conduction is depend on the four factors. So it is the conductivity of the body or the material. What is the heat transfer area? When we call the heat transfer area, it is what? The area on which the heat transfer takes place. That is, what is the direction of heat flow, and that direction of the heat flow perpendicular to the area. Another part is the thickness of the body and what is the temperature difference. And as we know, the temperature difference is the driving force for the heat transfer. So that is a part of the conduction. Now what is in convection? So there are the number of properties, number of things which it's affect the heat transfer rate by the convection. As the convection is very complex process comparing to the conduction one, there are the number of parameters to be considered here to getting the values. We learn the significant parameter in convective heat transfer such as the momentum diffusivity and the thermal diffusivity. We will learn what is the thermal diffusivity and the momentum diffusivity in the convective heat transfer. We will learn the dimensional analysis of the convective heat transfer. Now what is the dimensional analysis? As earlier I said, the convection heat transfer is a complex one. So there are number of factors which are affecting the heat rate, right? So in this case, if say there are the 10 number of factors which are affecting the convective heat transfer. Now the 10 numbers, it is very difficult to calculate the things. There is a complication in the equations. Okay, so what we do, we are just making a dimensionless number, and that dimensionless number we are the interconnect means what? We are comparing or making the equation of dimensionless number, and because of that, what happened, we can easily get the values and the equations for it of that conditions. So in the dimensional analysis, we can take the natural convection. What is the heat transfer rate when the dimensional analysis, where it is a natural convection, and we look for the forced convection too. So the two derivations based on the natural convection and the forced convection, as we are dividing the convection heat transfer in two parts, the natural convection as well as the forced convection. So we will see the definition of what is natural convection and forced convection. After that, we will learn the convective heat transfer correlations for the internal flow and external flow. So the heat transfer takes place internal flow as well as the external flow. The internal flow means, if take the circular pipe from which the liquid is flowing, a hot liquid is flowing, and there is exchange of heat between the surface of the pipe and the surrounding, then we call it is the internal flow, convective heat transfer. And one is the external flow. It is if you consider the flat plate, and on that flat plate, if the heat transfer takes place to the surrounding, then we call it is external. So it is it is to be learn the internal flow as well as the external flow. Also, we learn and see the various correlations for heat transfer by natural convection. Now, the correlations for the forced convection and correlation for natural convection are different because the parameters of natural convection and the parameters for the forced convection are different. Okay, so we see various correlations for it. There are a number of correlations in the for the heat transfer by natural convection. And the last topic that we are learn from this module, it is the equivalent diameter for a heat transfer. Now, what is this equivalent diameter? This equivalent diameter also we call it is the hydraulic diameter. You can call it as equivalent diameter or you can call it a hydraulic diameter. Now, why this is very important and why we are calculating the equivalent diameter for the heat transfer. Now, the geometry may be the different. I give the example. If you have to calculate what is the Reynolds number. To calculation of the Reynolds number, we have the formula. It is du rho by mu. D is the diameter, u is the velocity, rho is the density, and mu is the viscosity. Now the D is the diameter of the pipe. Okay, so we can easily get the Reynolds number, and as we know the Reynolds number, then we can easily distinguish whether the flow is the laminar, it is transition, or it is turbulent. And in the convective heat transfer, right, in the convective heat transfer, the laminar and the turbulent, the pattern of the flow is affecting the convection heat transfer. Okay, so it is very important to know what is the type of flow, the pattern of flow. Okay, and for that one, it is very important to know the equivalent diameter. Now, if it is a circular pipe, there is no problem. The D we can easily put it and see what is the Reynolds number. But what happens if it is a rectangular duct? If it is a rectangular duct, can we use the same formula here to calculate what is the Reynolds number? Then definitely we are not use that formula. We calculate instead of the D, we are taking the D equivalent. So first we have to calculate the D equivalent, and on that basis we can get what is the Reynolds number, and then we see the pattern of it. Okay, so this is very important for us to calculate the equivalent diameter. So in this module we learn the fundamentals of the convective transfer. We learn the various parameters, the significant parameters, that is the momentum diffusivity, thermal diffusivity. We learn the dimensional analysis and the derivation on it, that is on natural convection and the forced convection. We will take the correlations on the internal flow as well as the external flow for the forced convection. We we will learn the correlations for the heat transfer by natural convection, and lastly the equivalent diameter. So let's see the first, the convection. There are the two types of the convection. The first one is the free or natural convection, and the second is forced convection. Now, what is free or natural convection? When the fluid flow naturally by the density difference, the buoyancy force, the buoyancy are act on it, that we call it is a free or natural convection. And the forced convection, when forcing the fluid to give a motion to flow, that we call a forced convection. So in the convection, when we talk about the convection, as we know that the convection, the heat transfer by the convection takes place in the fluid. The fluid is gas and the liquid. Okay, the convection part is maximum the heat transfer by the convection in the fluid, not in the solid. The conduction is mostly the heat transfer takes place by the conduction in the solid, but in the liquid or in a fluid, it is by the convection one. And when the fluid is in steady state and when fluid in a motion, the heat transfer rate are different. Even the pattern of the flow or the velocity, it may affect the convection heat transfer rate. Okay, so this is a forced convection and natural. So let's see a diagram for it. So look at this diagram. So here it is showing a hot plate having a temperature of 50 degrees Celsius. The Q heat transfer rate takes place as a Q. Around surrounding the plate there is a air, a cold air. So here what happened, if you see the direction of the air to flow on this plate, it is like this one. So the cold air is contact to the hot surface, it gain the heat and then it move upside. It is not move in this x direction or in y direction, it is move upside. Similarly, from this side, when the cold air is contact with the hot plate, it is absorb the heat and then it move. Why it is move upside? Because if you see the density of the air at normal temperature, say 30 degrees Celsius, and when it is reached this the 30 degrees Celsius molecule, when it is touched with the hot surface, it gain the heat, and once heat is gained, it is the lighter because the density at 30 degree and density at 50 is different. At 30 it is more dense and the molecules at 50 it is less dense, and because of the changing the density, because of the lighter weight, it move upside and the cold air occupied the space. So this is the pattern of the flow when it is takes place by natural convection or the free convection. We are not forcing this air to flow on the surface. So this case we call it is the natural convection. So it is this pattern of flow takes place just because of the density difference of the air molecules. The density at 30 degrees Celsius and then density at 50 degrees Celsius is different, and because of that such type of the pattern of flow of air takes place in the natural convection. Now opposite to this one, a forced convection. Now the same thing, we are taking a plate having the 50 degrees Celsius is the temperature, the Q is the heat transfer rate, okay, and here we are using a fan, and the temperatures we maintain, okay, and the velocity we maintain 5 meter per second, okay, and the air is flow on this surface. Now here the pattern of flow of air is in the x direction. It is now not move upside because this fan is forcing the fresh air having a temperature, and it is reached to this surface and then it move away from it. And here the molecules is not stick here, it not be stay for a time. As it reach, it may move upside because another molecule is forcing him to move away from it, and because of that what happens, there is a larger molecules comes in contact and the more heat transfer rate takes place in this situation rather than this situation, because the air is contact here, molecules gain the heat, and after gaining the heat, once it is reached at the temperature where it is try to rise, and then only it can be move upside. But this is not a case, it may be the gain 30 degrees Celsius temperature and the molecule move away from it. It is not necessary to reach up to the 50 and then it is move away from it. No, because the fan is forcing the air molecules to move upside. So this is the difference between the forced convection and natural. So we are naturally the heat transfer takes place in this case, and here we are forcing them to do it. So the example for the forced convection, we can use the pump, we can use the agitator in the reactor to moving the particles. Because of the motion, it is a more heat transfer rate. Thank you very much for watching this video.